Let's take a look at the idea of taking the limit of a vector function. We know how to take the limit of a regular function on R2. How do we take the limit of a vector function? So let's start off by saying if R of t, this vector function, is defined as being equal to, in component form, f of t, g of t, and h of t, then the limit as t approaches a of R of t is equal to, in component form, the limit as t approaches a of f of t, the limit as t approaches a of g of t, the limit as t approaches a of h of t. So in other words, well, actually I need to add one more thing here. We need to add to this provided each limit exists. If just one of these limits does not exist, then the limit of the vector function does not exist. What this is saying is this actually means that the limit of a vector function is simply the limit of each component function. Okay, let me say that again. The limit of a vector function is equal to the limit of each component function. So with that in mind, let's take a look here at an example. Let's find the following limit, of course, if it exists. I want to find the limit as t goes to 0 of r of t, given r of t equals this function here. Well, what I'm going to do is I'm going to jump right into this and just simply take the limit of each individual component function. But I'm going to start off by saying, just for completeness, the limit as t approaches 0 of the vector function r of t is equal to the limit as t approaches 0 of e to the t minus 1 over t, the limit as t approaches 0 of the square root of 1 plus t minus 1 over t, and the limit as t approaches 0 of 3 over 1 plus t. So now, take a look at these one by one. First, I need to take a look at the limit as t approaches 0 of e to the t minus 1 over t. As you can see, this actually goes toward, well, e to the 0 is 1, 1 minus 1 is 0. This goes to 0 over 0, which is an undeterminate form. An indeterminate form. So I'm going to apply L'Hopital's rule. And take the derivative of both the numerator and the denominator and say this is actually equal to the limit as t goes to 0 of e to the t over 1, which is, as t goes to 0, it's 1 over 1, which equals 1. Now, the second one, I'm going to take a look at the limit as t goes to 0 of the square root of 1 plus t minus 1 over t. That goes to, again, as t goes to 0, I have 1 minus 1 in the numerator, which is 0 over 0. So this goes to 0 over 0, which is also an indeterminate form, or not also, but another. So again, I'm going to use L'Hopital's rule. And I'm going to consider the limit as t goes to 0. The derivative of the numerator is going to be 1/2 1 plus t to the negative 1/2. The derivative of the denominator is simply 1. Now, as this goes to 0, this goes to 1/2. And see this last one here, I need to take the limit as t goes to 0 of 3 over 1 plus t. That's obviously 3 over 1, that's just 3. So, what is the limit? The limit as t goes to 0 of my vector function r of t is equal to 1, 1/2, 3. Okay, limits of functions, of vector functions obey the same rules as real value functions, such as, you can use L'Hopital. Basically, all the rules that we deal with before in taking derivatives, we can apply them because we're taking, I'm sorry, I said derivatives, I meant limits. Because we're applying limits to real valued functions. So, of course, function by function, all of those techniques will apply. So this, in a way, is going to end up being a review from early Calculus 1. Now, this brings us to the definition of a continuous vector function. The vector function R of t is continuous at some value a if the limit as t approaches a of R of t is equal to R of a. This is actually simply saying that the vector function is continuous at a only if the component functions are continuous at a.